Hello everyone. Welcome to this lecture in the Build Large Language Models from Scratch series. Today, what we are going to do is we are going to construct the entire GPT architecture, or put in other words, we are going to code the entire GPT model. We have been building up to this lecture for a pretty long time now. So let me just quickly recap what all we'll be covering in today's lecture and what we have completed previously. So, in the previous set of lectures, which started around 4 to 5 lectures back in this GPT architecture or LLM architecture lecture series, we started out with a dummy GPT model class. So, when we started around 4 to 5 lectures back, we did not have an understanding of the building blocks of the LLM architecture or the GPT architecture. Slowly, we worked our way towards it. Initially, we learned about layer normalization. We wrote code for it. Then we wrote a code for the feed forward neural network along with the JLU activation. Then we learned about shortcut connections and wrote code for that. And in the previous lecture, we also wrote the code for the entire transformer block, in which the layer normalization, the JLU activation, the feed forward neural network, and the shortcut connections all come together. Today, what we are going to do is we are going to write code for this final piece of the puzzle, which is how point number one, point number two, three, four, five, and six essentially come together to form the entire GPT architecture. Throughout these 4 to 5 lectures on the GPT architecture, we have this, or we should have this visual figure in our mind. So here is what happens in the GPT architecture. We have text which gets tokenized. We have the dropout layer over here, and then the input embeddings are essentially passed to this blue colored block, which is called as the transformer block. In the previous lecture, we coded out all of these individual elements, which I'm marking in yellow right now in the transformer block. And we saw that when you give an input to the transformer, how to code out all of these blocks and how to stack them all together so that we get the output. Today, we are also going to learn about these final two steps, which is another layer normalization layer and another linear output layer towards the end. And we are going to see how do we post process the output from the transformer to get an output from the entire GPT model. That's the main goal today. So if you look at the overall picture, the masked multi-head attention is the key component of the transformer block, and the transformer block is the key component of the entire GPT model. We have coded out the transformer block, right? That's fine, but now we have to code out the entire GPT model. So we'll start from the bottom. We'll start from uh, this input IDs, or rather input text. We'll tokenize it. Then we will integrate the dropout, and then we'll integrate the transformer building block, and then we'll also integrate these final two building blocks. So you can think of this lecture as an assembly lecture where different moving pieces of the GPT architecture will all come together, and ultimately you will have a system in which, or ultimately you will develop a model which receives an input. So the input is in the form of text tokens, and the output from the model looks something like this right now. In the next lecture, we are going to see how to decode this output to predict the next word. So the main goal of the GPT model is to take an input text such as every effort moves you, and to predict the next word. So we are training the model for the next word prediction task. Today we are going to take Today I am going to take you all to this stage where we get this final output, and in the next lecture we are going to see how to get the next word from this final tensor. I'll assure you that the final tensor which we will obtain today can be easily used to decode the next word. So the main task today is how to go from the transformer output to this final output tensor from the GPT model. And we are also going to take an hands-on example and show you how the operations stack up throughout this entire GPT model. Okay, so when we started this lecture series, we actually started with this dummy GPT model, which I'm going to show you right now. So we started this lecture series with this dummy GPT model class right over here. And at that time, we had left several aspects blank. So we had left the transformer block blank. We had also left the layer normalization class blank. We had coded out some aspects of the forward method, but most of these classes were blank. But that's fine. Now we are ready to fill up these different aspects so that we can return the output. So ultimately, we are going to see this entire workflow today. We are going to have the input IDs, which will be converted into token embeddings. Then we'll add positional embeddings. We'll add the dropout layer. We'll pass the output of the dropout through the transformer block. Then the output from the transformer block will be passed through another layer, normalization layer. And then we'll finally have an output head layer and we'll return the logits. Don't worry about understanding all of this right now. I'm going to sequentially take you through each of this step by step and explain to you what exactly happens in each of these code lines. Okay, so what we are essentially going to do is that since we coded this transformer block last time, we can replace this with the actual transformer code. We have also coded this layer normalization block in one of the previous lectures. So we'll replace this with the layer normalization code. Okay, so the goal, now we are ready to achieve the goal of today's lecture, which is to assemble a fully working version of the original 124 million parameter version of GPT-2. So we are going to do a pretty awesome thing today. We are going to take input texts and then we are going to pass them through this entire GPT-2 architecture, which by the way has 124 million parameters, and then we'll get the output tensor. And all of this we'll be doing on our local computer. I'll be sharing the code with you so you'll be able to execute it on your own end. That's pretty awesome, right? You'll be probably running a large scale, large language model for the first time on your local machine. So, you, at this moment, if you have followed the previous lectures, we are going to assemble several components here. So, people who have followed the previous lectures, this lecture is going to be very enriching for you. If you have come to this lecture for the first time, I've designed it so that you can follow it along. But please understand that the value which you will derive from this lecture will be significantly higher once you have also gone through the previous lectures. Okay, I hope all of you have this visual map in mind. We are going to do all of these steps which are shown in this visual map today and with actual parameters from GPT-2. We are going to use around 124 million parameters today. Before I dive into code, I want to first show you everything on this whiteboard, especially in terms of dimensions, so that you get a clear understanding of what is exactly happening when we are going to move to code. I've seen that many students who learn about large language models, they are very unclear about how the dimensions work out. So what I've actually done is that I've made this flow map over here. So I'm just zooming out here right now. We are going to go through all of this in just a moment, but this is the flow map which I am going to teach you right now. And the blocks which you see on the screen, they are mostly there to represent the dimensions of the input, the dimensions of the output. So my goal here is to visually convince you of what exactly is happening in the GPT model so that the code becomes significantly easier. The code for this GPT model is actually pretty simple and straightforward. The only difficulty which students face is that many tensors come into the picture, many dimensions come into the picture, and students get confused as to they cannot visualize what's going on. And I've not found too much good material out there which takes students through every single step in the GPT model like this. Even in the previous lecture we went through the entire code, but we did not see this hands on example of, let's say, if you take a specific input sequence, how does that input sequence flow through the different blocks of the GPT model and how do we get the output. Let's dive into every single detail. Remember, the name of this whole playlist is building LLMs from scratch. We are not going to assume anything. I want to teach you the nuts and bolts of how every single line of code works. And that's why I have made this effort to construct this visual flowchart. Okay. So let's say the input is every effort moves you, right? And then we have to make the output prediction, which is the prediction of the next word. And the next word is forward. Every effort moves you forward. So let's go through a sequence of steps of what exactly happens in the GPT model when this input is given. I'm going to switch color right now to a darker color so that you all will see what I'm writing on the board. Okay, so ideally inputs come in batches. So what we are going to do is that, let's say when we go to code, we'll see that we have two batches. and in each batch there are four tokens. So the first batch has every effort moves you and the four token IDs corresponding to that, and the second batch has token IDs corresponding to the second sentence. For the sake of simplicity, right now I am just going to analyze the first batch, and then the same learnings which I'm going to show you can be applied to the second batch as well. So I'm getting rid of one dimension, which is the batch dimension for now, for the sake of simplicity. So we are going to focus only on these four words: every effort moves you and prediction of the next word. The first step is that, remember that we have a vocabulary, right? Even when GPT-2 model was constructed, we have a vocabulary, and the vocabulary size is 5 50, I think it is 50257. So 50257 is the vocabulary size for GPT-2. So the first step is you take every word and you map it to a token ID. In the vocabulary, every token is mapped to a token ID. So these are the four tokens. For the sake of simplicity, think of every one token equal to one word. That's not at all what's happening in the GPT-2, because GPT-2 uses byte pair encoding, which is a subword tokenizer. We have a separate lecture for that, where you can see that even characters and small subwords can be tokens. But just for the sake of simplicity, I'm going to use one token equal to one word interchangeably in today's lecture. Okay, so we are looking at this first batch which has four tokens or four words. That's the first step, to convert these tokens into these four token IDs. Awesome. The next step is actually to take these token IDs and to convert them into token embedding vectors. So this is a key point here. Computers can't understand words, right? And it does not make sense to just have token IDs, because we need to capture the meaning between words. Dog and puppy are close to each other. Cat and kitten are closer to each other. It turns out that representing words in a vectorial format can help preserve the semantic meaning between words. So the first step is to convert every input token into this token embedding vector and to decide an embedding size. So we are using an embedding size of 768 because that was the embedding size which was used for the smallest GPT-2 model when it came out. So if you see, every, which is the first token, is now encoded as a 768 dimension vector over here. Effort, which is the second token, is also encoded as a 768 dimensional vector. Moves, which is the third token, is encoded as a 768 dimensional vector. And U, which is the fourth token, is also encoded as a 768 dimensional vector. One point which I want to mention here is that this encoding, we do not know what's the best encoding from the start. We are initially going to project these vectors randomly in the 768 dimensional space, and then we are also going to learn the token embedding parameters. In GPT models, along with everything else, the token embedding, all the embedding parameters are learned. So right now, let's say I told you about cat and kitten, right? When we start out, the vector for cat and the vector for kitten is initialized in random directions. But when the model is trained, when the embedding vectors are trained, they will be closer together, they will be more aligned. So right now, for every uh, for the token every, for the token effort, for the token moves, and for the token u, we randomly initialize vectors in the 768 dimensional space. That is the first step, token embedding. The second step is that, remember, along with the semantic meaning of words, what's also important to capture is where the word comes in the particular sentence. So every effort moves you, and every comes in position 1. Effort comes in position 2. Moves comes in position 3, and you comes in position number 4. So along with representing the words themselves as an embedding vector, we also represent every position as an embedding vector. So we are considering four positions here, right? Which also becomes the context size. Remember, the context size is the maximum number of words which can be used to predict the next word. In our case, the context size is equal to 4, which means only four positions matter. So that's why in the positional embedding, we are going to look at the embedding vectors for four positions. Position number 1 has again a 768 dimensional vector. Position number 2 has a 768 dimensional vector. Position number 3 has a 768 dimensional vector. And position number 4 has a 768 dimensional vector. Similar to token embedding, we actually do not know the embedding values in each of these positional embedding vectors. These embedding values are initialized randomly initially. We do not know what these embedding values represent. These will be trained as the during the training procedure. But the important thing to note is the embedding size. The embedding size for every vector in the positional embedding is 768, and this is the same size as the token embedding. And the reason for this is, in the third step, what we are going to do is that we are going to add the token embedding for each token along with the positional embedding. So if you go to step number 3, which is seen on the screen right now, let me zoom in further. For the first word, which is every, it's in position 1. So we are going to take the token embedding for every and we are going to add it with the positional embedding for the first position. And the result is the input embedding for the first token. So since the token embedding and positional embedding have the same dimensions, the input embedding also has the dimension of 768. So this is the input embedding for position. Then effort. So when you come to effort, which is the second word, it's in second position. So we take the token embedding for the second word and we add it with the second positional embedding for the second position, and we get the input embedding for the second token, which is effort. And here again the embedding size is equal to 768. You can see over here, which I am marking right now in purple color, the embedding size for the uh, second position, or the input embedding size for the second token is 768. Now we move to the third token, which is moves. This is in position 3. So we'll take the token and add the positional embedding vector for position 3, and that leads to input embedding vector for moves, which has an embedding size 768. Similarly, for the fourth position, which is U, we take the token embedding and add the positional embedding, and we get the input embedding, which has the size of 768. This is step number 3. Remember, this is a very important step. Token embeddings plus positional embeddings leads to the input embeddings, which this formula I have also written over here. Input embedding equal to token embedding. Uh, Input embedding equal to token embedding plus the positional embedding. Okay, so that's the step number 3, and after these steps are completed, we move to step number 4. Step number 4 introduces dropout. So what happens in dropout is that until now we have input embeddings for every word, right? We have input embeddings for every effort, moves, and u, and the embedding size is a vector, so which means that for every token we have the input embedding of 768 sized vector. In dropout, what happens is that we randomly turn off some elements of every input embedding to 0, and that's specified by the dropout rate. So if the dropout rate is 50%, from every embedding randomly 50% of the elements are turned off to 0. So let's say this might be turned off, this might be turned off. So 50% of 768 is around 384, right? So around 384 elements of each input embedding are turned off to 0. And this is done for every token. So here I am just showing the random elements which are turned off to 0. Remember, this is probabilistic. So when I say 50%, not exactly half of the embeddings will be turned off to 0. On an average, 50% of the input embeddings will be turned to 0. Okay, so why is dropout implemented? The main reason why dropout is implemented is to prevent overfitting, improve generalization, and this generally helps a lot. The main dropout technique was initially implemented in neural networks to prevent some neurons from being lazy. So during training, sometimes what happens is that some neurons don't learn anything and they depend on other neurons, and that leads to problems in generalization. So what people do is that they implement dropout layers where neurons are turned off randomly. So the neurons which were lazy earlier have no choice but to learn something, and that improves the generalization performance because every neuron is generally trying to learn something. And that's the similar case for here also. Wherever dropout is implemented, the main reason for implementing dropout is to prevent overfitting or to improve generalization performance. Okay, so we have seen 4 steps up till now. Let's recap them. The first step is token embedding, which we saw. The second step is positional embedding, which we again saw. The third step is input embedding, which is essentially adding the token embedding plus the positional embedding. And the fourth step is implementing dropout. Now remember, up till here the transformer block has not been introduced at all. We are still outside the transformer block. So let's go to this overall structure of this transformer block again to see what all we have seen up till now. So if you look at this structure until now, um, let me zoom in further. Yeah, if you look at this structure until now, we have seen the four steps which come before here. So we tokenize the text into input IDs, then we add then we have the token embeddings, which was the first step. Then we add the positional embeddings, which was the second and third steps. We get the input embedding, and then we apply the dropout. So we have seen these four steps until now. We are at this point. And after the dropout, now we will enter the transformer block in which all of these steps will be performed. So let's go to step number 5 right now, where we'll be looking at the transformer block. Okay, so when we reach the transformer, these are the input embeddings which we have. So these are the input embeddings with dropout. One thing which I would like you to see is that the dimensions are being preserved. So when we started this at the first step, these were the same dimensions, right? Every token had the dimension embedding dimension of 768. And when we enter the transformer block, every is still a 768 dimensional vector, effort is still a 768 dimensional vector, moves is still a 768 dimensional vector, and u is still a 768 dimensional vector. The one thing which has not happened is that until now every vector only contains meaning about itself, but we do not know, let's say when we are looking at every, how much information, how much attention should we give to effort, moves, and u to predict the next word. That's very important, right? Along with capturing the semantic meaning which vector embedding does, it does not capture the meaning of how, let's say, each word is related to other words. So let's say when we look at effort, and we want to see, when we are looking at effort, how much attention should we pay to every, moves, and you when predicting the next word. That information is not captured, and that will be done through the attention block in the transformer module. Let's see when we get to that. So now we are at this stage where we have the input embeddings with dropout. Then we apply the first layer in the transformer block, which is the layer normalization. So this is also called as the layer norm. What this layer normalization will do is that it will look at every token. So let's say I'm looking at this token every, uh, and then it will look at all of these values here, and it will normalize the values so that the mean of these values is equal to 0 and the variance of these values is equal to 1. And this will be done for every single token. So after we do it for the token every, we then move to effort. So we'll take all of these embedding values and we will normalize them. So we'll subtract the mean from every value and divide by the square root of variance. And this same procedure, normalization procedure, will be done to moves and to u. So after the layer normalization is done, when we look at every token and when we look at the values present in the embedding, we'll see that the mean of those embedding values is equal to 0 and the variance of those embedding values is equal to 1 for every single token. Layer normalization is performed to improve the stability during the training procedure. Okay, after layer normalization is performed, the most important step, which is actually the engine of the transformer block, which is why LLMs work so well, is this masked multi-head attention. What is done in this module, in this step, is that we take the embedding vectors and we convert them into context vectors. So if you look at the output of the mask multi-head attention, the size of the output is same. So for the word effort, let's say, we still have an embedding of 768 dimensions, but now this is called as the context vector embedding. The reason is called context vector is that, along with capturing the semantic meaning of effort, which the vector embedding already did, this context vector which exists for effort also captures the meaning of how much attention should we give to every, how much attention should we give to moves, and how much attention should we give to you when we are looking at effort. So the context vector for every token captures the meaning of how much attention should be given to all the other tokens in the sentence. That's why it's called attention. This is by far the most important step in the entire GPT model. Without this part, LLMs would not perform as well. This part really tells us that when we want to predict the next word, which are the important words to look at, what is the meaning between different words, how do different words attend to each other. So the context vector which I have written here, it looks very simple right now, but we have devoted 5 lectures of 1 hour, 1.5 hour each to understand this one step. which appears in the whole GPT model. Because here is where the real magic happens. Here is where we transfer uh, vector embeddings into context vector embeddings. So we capture meaning, we capture context as to how different tokens or different words are related with each other. Awesome. So until this step, here again you can see the dimensionality is mentioned, is preserved throughout. That's what I like about the GPT model. So for throughout every step, you will see that we still have four tokens and the dimension of each is 768. This really makes the GPT model scalable. It's much easier to add multiple modules together because addition of modules does not change the dimensionality. Then after multi-head attention, we again have a dropout layer which randomly turns off certain um, certain context vector values to zero. So here I have shown the color red, where the values of every we look at every token and we randomly switch off certain values to zero. It's the same dropout layer which we had seen earlier. Then we actually have a shortcut connection. So wherever shortcut connections are mentioned, it means that the output of this layer, the output of the dropout layer is added back to the input which we started with to the transformer. This input, the output is added back, and the reason it's done is because it provides another route for the gradient to flow and it prevents the vanishing gradient problem, which means that the training proceeds in a much smoother manner. So after the shortcut connection is applied, that does not change the dimension at all. We again apply one more round of layer normalization. So again, we look at every row. The mean is uh, changed to zero. The variance is changed to one. So that's how every values is normalized. We subtract the mean from every value, divide by the standard, divide by the square root of the variance. So that finally, when we look at the values together, their mean will be zero and their variance will be one. This is done for every single token. And then after the layer normalization layer, we have a feed forward neural network. So when you zoom into this network, you will see that this is kind of like an expansion contraction network where, let's say, you have the inputs, right? So we process every input step by step here. If you first look at the first token, which is every, it's a 768 dimensional token, right? If you see the input which enters this feed forward neural network is that every token has a dimension or an embedding size of 768. So what happens in this neural network is that we look at each token sequentially. So let's say we are looking at the first token, which is every. Let me zoom into this neural network a bit. Yeah, so first we project this input into a higher dimensional space. In fact, this neural network has one hidden layer, and the number of neurons in this hidden layer is 4 times 768, which is 4 times the embedding dimension. And then we contract back to the original dimension. So the output from this neural network is the same dimension as the input, but there is this expansion and contraction which is happening, and that allows a much richer exploration of parameters. That makes our LLM much better at prediction of the next word since it captures the meaning in a much better manner. So if you look at the output from this neural network, the output from this neural network is the same size as the input which entered it. We have four tokens and the embedding size is equal to 768. Uh, but this expansion contraction which you see over here, the arrow which I'm showing here is the expansion. The arrow which I'm showing now is the contraction. That is the key, because since the middle layer has huge number of neurons, it has four times the embedding dimension neurons, which is 4 times 768. The number of parameters are huge in this feed forward neural network. That allows for a richer exploration space. After this feed forward neural network, we have another dropout layer which randomly switches off certain values to be equal to zero, which I have just shown here again uh, by the red color. So in every token, random values are set to zero. Typically, one dropout rate is mentioned at the start, and that's applied everywhere where these dropout layers are implemented. Then we have another shortcut connection where we basically add the output uh, after this dropout to the input when we entered here. So this is the input in this second row. So the input which was there here is added to the output of the dropout layer which we are seeing over here, and that's why it's a shortcut connection. and then the output from the shortcut connection is our transformer block output over here. So right now, the transformer block output which I'm highlighting is the output after so many steps in the transformer block. So if you look at the dimensions of this output, you'll see that every token is again a 768 dimensional vector over here. So the dimensions are exactly the same as the input to the transformer block. So let me zoom out a bit here, and you can now try to appreciate the number of steps which are involved in the transformer. So if I zoom out here, and if you look at the right side of the screen along with me, let me actually move it to the center. Yeah, so these are all the steps which are involved in the transformer right now. Whatever you are seeing on the screen, let me minimize this color. Yeah, I hope you can see the entire transformer workflow on the screen right now. We start with the layer normalization. So I'll show this with a different color probably. Yeah, we start with the layer normalization, then we move to the mask multi-head attention, then we have a dropout layer, then we have a shortcut connection over here. Let me mark this line. Yeah, we have a shortcut connection over here. Then we have another layer, normalization layer. We have a feed forward neural network. We have a dropout layer. Then we again have a final shortcut layer, which actually takes us to the transformer block output. Now let us actually go to the visual diagram again to see whether we indeed have implemented all the steps which were mentioned in the transformer block. So I'm zooming in over here right now, and if you see, there are actually 1, 2, 3, 4, 5, 6, 7, 8 different steps, right? We start out with the, again let me switch to a different color here. Yeah, yeah, we start out with the layer norm, we go to the multi-head attention, we go to the dropout, we have the shortcut connection. That's the first block. Then we have again the layer normalization, the feed forward neural network, the dropout, and then the last shortcut. So there are 8 different steps here, which were the same 8 different steps we implemented in the visual flow map. And now there are the final 2 steps which are remaining. So let's look at the last 2 steps of the GPT model in the visual flow map. So the fifth step was the transformer step, which we implemented. Within the transformer also there were 8 different steps. Now we go to the next block, which is the next block is another layer of normalization. So the transformer block itself has 2 normalization layers, but we have another normalization layer after the transformer block output. So here we have the transformer block output, and here you can focus on the dimensions. Again, every vector or every token has an embedding size of 768, right? Again, the dimensionality is preserved, and then we apply the layer normalization. So same thing as what the layer normalization does is done here also. In every token, we normalize the embedding values so that the mean of the resultant embedding values is 0 and the variance is equal to 1, and this is done for all the 4 tokens. So again, the layer normalization does not change the dimensions. And then the last layer which we have is the output head. So the output head is a neural network at the final stage of the GPT model. So the input to the output head is this input, which has 4 tokens, and each token has a dimension of 768. Then what we do is that we pass this through a neural network whose size is the embedding dimension multiplied by the vocabulary dimension. And I'll tell you why just in a moment. But if you take this input tensor, and if you pass in through the neural network which takes in inputs of 768 dimensions, and the output is 50257, the resultant uh, output which you get, it's called as the logits matrix. And this logits matrix actually has 4 rows, because we have 4 tokens. Every effort moves you, and the number of columns here is not equal to 768. The number of columns is equal to the vocabulary size, because we are passing the input through a neural network whose final output size is 50257. So for every token, we have this logits, which is a 50257 dimensional vector. So for every there is a 50257 dimensional vector. For effort, there is a 50257 dimensional vector. Similarly, for moves and u, there are 50257 dimensional vectors. And the reason here is because we want to predict the next word, right, based on the input. So when every is the input, we want to predict what's the next word, and that should be effort. So we look at the vocabulary and we look at that token or that column which has the highest value, and that column should ideally correspond to effort when every is the input. Similarly, when every effort is the input, we will look at the column which has the maximum value, and that column corresponds to certain word in the vocabulary, and that word should be moves, because when every and effort are the input, moves is the output. Similarly, when we look at every effort moves as the input, we will predict the next word, and that should be u. So we look at that column which has the highest value, and that should hopefully be u. And finally, we look at every effort moves u. That is the final prediction task. And then when every effort moves u is the input, we look at the final output, and that should hopefully be the token which corresponds to the next word, which is forward. Every effort moves you forward. We'll see how to make the next word prediction in the next class. But for now, I just want you to appreciate that this last step is the only step where the dimensions of the input change. The dimensions of the input all along were 4, which were the number of tokens, multiplied by 768, which was the embedding dimension. But now the final output size is 4, which were the number of tokens, multiplied by 50257. And based on this final output, we'll get the next word prediction. Now when you look at every effort moves you, the context size is 4. Whenever we have a context size, we have that many prediction tasks. So remember, here there are 4 tokens, right? So we don't only have one prediction task. You might think that the only prediction task is every effort moves you is the input and we have to predict the next word. No, there are 4 prediction tasks. The first prediction task is every is the input, then effort should be the output. Every effort is the input, moves should be the output. Every effort moves should be the input, you should be the output. And only the fourth prediction task is every effort moves you, what's the output. So that's why we have these 4 rows here, because there are 4 prediction tasks. We'll see in the next class how to predict the next word from this output tensor which we have obtained. Now one thing to mention is that so here if you see, the output tensor value will actually be 4. So let me write this down over here. The output tensor value will be 4 multiplied by the vocabulary size, which is 5. So it's 502 5 and 7. So that is the final tensor value. Remember, one thing which I have considered here is only one batch. If you have 2 batches, this will be the final tensor generated for both those batches. So similar to every effort moves you, if you have another sentence of 4 words such as I like uh, movies and you have to predict the next word, that's the second batch. So then the output tensor will also include the batch size. So then it will be 2 multiplied by 4 by 50257. Why this initial 2? Because the batch size is equal to 2. So the first dimension is always the batch size. The second dimension is the number of tokens which we have, or the context size. And the third dimension is the 50257, which is the vocabulary size. So this is the output tensor dimension format which we have. Now let me zoom out here and show you the entire flow map which we have seen. It was a pretty long flow map, but I hope you all have understood what we were trying to do over here. The reason I went through this entire flow map, starting from token embedding, positional embedding, to input embedding, to dropout, to the transformer block, then we went to layer normalization, then finally we went to output head. The reason I showed you all these things is just so that you understand dimensions and what's going on with dimensions. I did not just want to show you the code, because when you see the code, you cannot visualize the dimensions. But now, once you have seen this lecture, and whenever you, let's say, you're looking at the layer normalization part of the transformer, right? You can just visualize what's happening. Uh, what are the dimensions of the input to a particular block? What are the dimensions of the output? And so that will make your learning process much easier. So now actually on the whiteboard we have seen how the building blocks stack up for the entire GPT model. We started with tokenization, input embedding, positional, we went to transformers, and then we saw the final layer norm, and then we also saw the final linear output layer. Okay, so now once your intuition is clear, once your visual understanding is clear, we are pretty much ready to move into code. So now let us dive into code and see how these different blocks can be arranged together to code the entire GPT model. All right, so let's jump into code right now. Here's the GPT configuration. It's the same configuration as GPT-2, which we are going to use when we are going to look at this entire coding module. So here you will see that the vocabulary size is equal to 50257. This was actually the vocabulary size which was implemented when GPT-2 was trained. The context length is equal to 1024. The vector embedding dimension, which we also saw on the whiteboard, that is equal to 768. The number of attention heads is equal to 12. The number of transformers which are there, which we are going to implement, are equal to 12. The drop rate or the dropout rate is equal to zero point 0.1, and the query key value bias is false. This is for setting or initializing the weight matrices for the queries, the keys, and the values. We don't need the bias term in that. For now, you can focus on a couple of things. The first is the embedding dimension, which is going to stay 768 throughout. The second is the 50257 vocabulary size. These are the same dimensions which we just saw on the whiteboard, so you might be able to relate to them. 12 is the number of dropout. 12 is the number of transformer blocks. So in GPT-2, when it was trained, they had 12 transformer blocks. We are also going to use a similar number of transformer blocks. Then the number of attention heads. So every transformer block has a multi-head attention module, right? And that module has a certain number of attention heads. We are going to use that equal to 12. Dropout rate is zero point 0.1. I think this much should be enough to understand the entire code. Now, as we are going through this code, I want you to just keep this diagram in mind and the dimensions which we just saw in the visual flow map. Everything will follow from this particular diagram, since we are exactly going to code it in a similar manner. Okay, so we started out this lecture series 4 to 5 lectures back with this dummy GPT model class, where we had the forward method, but the transformer block was not implemented. So this was a dummy transformer block. The layer normalization was not implemented. This was a dummy layer normalization. What we did over the last 3 to 4 lectures is that we coded the layer normalization class, feed forward neural network class, and also the transformer class. So here's the layer normalization class which we had coded. Given a particular layer, now you can think of whenever you see layer normalization. Remember, we have seen the visual flow map now, right? So you can try to visualize what happens in the layer normalization layer. We have seen that already. So see, this is exactly what happens in a layer normalization layer. We look at every token that has 768 dimensions, right? Then what we are doing is that we are going to subtract the mean and divide by the square root of the variance, so that the resulting values have a mean of 0 and standard deviation or variance of 1. We also have a scale and a shift here, which are trainable parameters. Then we have the feed forward block. And remember where the feed forward block comes in the transformer architecture. It's this it's this feed forward block. Let me actually change my pen color to, it's this feed forward neural network which I've shown you over here, the expansion contraction feed forward neural network. This is that feed forward block. So you'll see that the input is the embedding dimension, the layer is 4 times the embedding dimension size, and the output is the embedding dimension. Once you are able to visualize this, you will be able to easily understand this code. The input is the embedding dimension, the hidden layer is 4 times the embedding dimension, that's the expansion layer. Then there is a contraction layer from the 4 times embedding dimension to the embedding dimension. And there is a JLU activation function. We spent a whole lecture on the JLU activation because it's a bit different than the ReLU. It's smoother on the negative side. I think I also have a plot for the JLU activation over here, so let me quickly show you that, if I can find it. Yeah. So on the right hand side, you can see ReLU. It's 0 for negative inputs. For the JLU, it's not 0, and also it's differentiable at x equal to 0. That's why in LLM training, generally the JLU activation is used. So we coded the layer normalization class, the JLU class, and the feed forward class. And then in the last lecture, we coded the entire transformer block class itself. So here we had the 8 steps in the transformer. If you remember, take a look at these 8 steps which we saw. Um, Let me zoom out here further. So these are the 8 steps which we saw in the transformer. We start with input embeddings, add a dropout, layer normalization, then we go to the mask multi-head attention, then dropout, and then the shortcut connections. That's the first of these 8 steps in the that's the first four of these 8 steps in the transformer block. Then what we do is that then we again have a layer normalization, feed forward neural network with JLU, then dropout, and then another set of shortcut connections. These are the last 4 steps. So overall, there are these 8 steps which are happening in the transformer block architecture, and it's the same 8 steps which we wrote down when we wrote the code for the transformer block class. These are the first 4 steps, and it ends with the shortcut connection. And these are the last 4 steps, and here again it ends with the shortcut connection. The main point which we also recognized when we implemented the transformer block class is that the dimensions are preserved. The dimensions of the input to the transformer are the same as the dimensions of the output from the transformer block. Awesome. Now we have all the knowledge, and now we are ready to code the entire GPT architecture. So first, let's look at the forward method, which takes in the input. And remember, the input looks something like this. Let me show you how the input actually looks like. The input might look something like this, where here we are showing 2 batches, and each batch has, let's say, 4 token IDs. So the number of rows here in this tensor are equal to the number of batches, and the number of columns are the sequence length, or the number of tokens which we are considering. That's why if you see, the number of rows here in the input shape are batch size, number of columns are essentially the sequence length or the number of tokens. Whenever now I'm explaining this next whole part, you can keep that flow map in mind which I showed you on the whiteboard, and think about the flow which we had for every effort moves you. So first we convert the tokens into token IDs, and then we convert the token IDs into embedding vectors. That's what's done in this token embedding. Uh, so we initialize an embedding layer from the PyTorch module, and then from this embedding layer we get the embedding token embedding vectors for the input IDs, and then similarly we get the positional embedding vectors for the 4 positions. So see, sequence length is equal to 4, so we get the positional embedding vectors for the 4 positions, and we add the token embedding to the positional embeddings. So whenever you try to make sense of dimensions here, always think of one batch at a time. When you think of one batch, things will be simplified, because one batch only has 4 tokens, let's say. So when you look at this step, the output of this step, uh, you can visualize the output exactly from the flow map which we had seen. So let me take you to that. Yeah, look at the first step over here, which was titled as positional embedding. When you look at this code, the token embeddings, these are essentially uh, these are essentially this kind of a tensor, where for every token you have the 768 dimensional vector. Similarly, you can think of the same visualization for positional embeddings. And when you look at this x equal to token embeddings plus positional embeddings, you can try to visualize this part which we saw. We added the token embeddings to the positional embeddings right over here. So for every token, we added the token embeddings and the positional embeddings to get the input embeddings. That's exactly what I've written in the code over here. And then after this part, we go to the next steps, which were the same in the visual flow. So the next step was addition of the dropout, which was step number 4 over here. I'm showing that with a star right now. That was the step number 4. So dropout layer followed by the transformer followed by the transformer block, and then the last 2 layers were another layer normalization layer, which was step number 6 here. This was the second last layer, which was another layer of normalization, and then the final layer was output head. So after you get the input embeddings, there are 4 things. You apply dropout layer, you apply the transformer blocks, you have the another layer of normalization, and then you apply the output head. That's it. Now if you see the transformer blocks, we are chaining different transformer blocks together based on the number of layers. So in the configuration we have seen that the number of layers is equal to 12, right? In this configuration we have seen that the number of layers is equal to 12. So we are actually chaining 12 transformer blocks together using nn dot sequential. This nn dot sequential is a TensorFlow or PyTorch module which allows us to chain different neural network blocks together. So we have chained 12 transformer blocks. So when you see the self.trf blocks, it just looks like one line of code, right? But there are actually 12 transformer blocks chained together here. And in each transformer block, there are 8 different steps which are being performed. So it's a huge number of operations being performed in this one simple line of code. That's it actually. If you think of the building blocks, if you have understood the transformer block, if you have understood the layer normalization class, if you have understood the dimensions with respect to the token embeddings, positional embeddings, that's all what the um, transformer or what the GPT model class is actually doing. It takes in the input and then the outputs are the logits which we saw on the whiteboard. So the dimensions of the logits, if you remember, let me take you to the whiteboard once more. So if you go to the whiteboard and if I zoom into this part of the if I zoom into this part of the whiteboard right now, you'll see that the output of the GPT model is this output logits. And the shape of these logits is for each batch we have the number of tokens. In this case, those were 4 tokens, and the number of columns are equal to the vocabulary size. And then the first dimension is the number of batches which we have. Okay, so now what we can actually do is that we can take a simple input batch and then we can pass in through this entire GPT model. So what we are doing here is that we are taking an input batch which has 2 batches and each batch has 2 tokens. What we are doing is that first we create an instance of the GPT model and pass in the model configuration, and then we create this object. So we create an instance of model which returns the output. So if you print out the input batch, you will see this. And if you print out the output batch, let's look at one batch currently. If you look at one batch, you will see that there are 4 tokens and each token has number of columns equal to the vocabulary size, which is 50257. This is exactly what we had seen in the output logits, right? So if you see in one batch, there are 4 tokens, 4 rows, and there are 50257 columns. This is exactly the same thing which is happening for the second batch also. There are 4 tokens here and there are 50257 columns because the vocabulary size is 50257. So as we can see, the output tensor has the shape 2 batches, 4 tokens in each batch, and 50257 columns. Since we passed in 2 input text and 4 tokens each, the last dimension 50257 corresponds to the vocabulary size of the tokenizer. In the next class, we are going to see how to convert these 50257 dimensional output token vectors back to tokens and how to predict the next word. But for now, you can see that the GPT model class which we have constructed is working fine, and there are a huge number of parameters which we are actually dealing with here. This small piece of code over here has more than 100 million parameters. Can you imagine that? There are just a huge number of parameters because there are 12 transformer blocks chained together. There are 8 steps in each transformer block. Then and remember, there is that expansion contraction layer in each transformer block. That layer itself has a huge number of parameters. We have parameters for token embedding, positional embedding, etc. So totally all of the parameters add up. We can actually print out the number of parameters. So what we can do is that we can have total params and we can do p dot numel. What p dot numel will do is that it will actually print out. So using the numel method, short for number of elements, we can collect the total number of parameters in the model's parameter tensors. So if you print out the total number of parameters, you will see that the number of parameters is equal to 163 million. Huge number of parameters, right? And all of this is running on our local machine. So you might be thinking, earlier we spoke of initializing a 124 million parameter GPT model, right? So then why is the actual number of parameters 163 million? Why is it so higher? So this actually relates back to a concept which is called wait time that is used in the original GPT-2 architecture. So which means that the original GPT-2 architecture is reusing the weights from the token embedding layer in its output layer. So if you go back to the whiteboard right now, yeah, in the schematic which we saw over here, there is an output layer, right? There is an output layer towards the end, and there is a token embedding layer over here. When GPT-2 model was constructed, the parameters which were used for the token embedding layer were the same parameters which were used in the linear output layer, and that's why the total number of parameters was less. In our case right now, we did not reuse the parameters. So when we print out the parameters, they say 163 million, but in GPT-2 architecture, they are reusing the weight. So we can actually print this out. So in our case, what we can do is that we can print out the embedding layer shape of the token embedding layer, and we can see that the embedding layer shape is 50257, 768, and we can also print out the output layer shape, and these both have exactly the same shape. So that's why when in GPT-2 model, they just reused these parameters. So what we can actually do is that we can remove the output layer parameter count from the total parameter count and check the number of parameters. So when the output layer parameters are removed, the total number of parameters comes up to be exactly 124 million parameters, which is the same size of the GPT-2 model. So weight tying actually reduces the overall memory footprint. From 163 million, we go to 124 million, and it also reduces the computational complexity of the model. However, using separate token embedding and output layers results in better training and model performance. That's why when in our code which we are writing, we are using separate layers in our GPT model implementation. And this is true for modern LLMs as well. Weight tying is good for reducing the memory footprint and reducing the computational time and complexity. But to get a better model training and performance, it's good not to reuse the parameters. We can also print out the space which is taken by our model. So we can compute the memory requirements of the 163 million parameters. So the total size of the model, it turns out it's around 600 megabytes of space. So in conclusion, by calculating the memory requirements for the 163 million parameters in our GPT-2 model, and assuming that each parameter is a 32-bit float taking up to 4 bytes, that's why we have multiplied by 4 over here. We have assumed that each parameter takes around 4 bytes, so we multiplied the total number of parameters by 4 to get the total size. That's 620 MB, which illustrates the relatively large storage capacity required to accommodate even relatively small LLMs. So GPT-2 is relatively small, 120 million, compared to there are now models which have more than a billion parameters. Imagine how much space such a model will take on your device. It's impossible to run extremely large models on local devices, and that's why we need GPU access. So in this lecture today, we implemented the GPT model architecture and saw that it outputs numerical tensors, right? So you might be curious, how do we go from that numerical tensor output into the next word prediction task? So that we'll be doing next. In the next lecture, we are going to generate text from the output tensor which we have obtained today. Today, what I want you to appreciate is just within 10 lines of or even 15-20 lines of code, we have actually run a very powerful large language model completely on our laptop, and we built this model from scratch. This model had more than 160 million parameters. It took 600 megabytes of space on our machine, indicating the size required by these models. And I want you to appreciate that once you understood the visual flow map I showed you on the whiteboard, it's just 8 lines of code. But to understand these 8 lines of codes, we need to put in a lot of effort, because there is a lot of theory and a lot of intuition behind every single line of code over here. But once you get that, it's just these uh, stacking of the token embeddings, positional embeddings, dropout layer, transformer blocks, another layer normalization, and the output head. That's it, and then we directly get the logits. I hope you are following these lectures. I know this lecture is also become a bit long, but it is essential to show you the theory as well as the code. In today's lecture, I could have directly showed you this code, which was only this much. But then at every step, you would not have visualized the dimensions. What is exactly happening? Can we take a specific example and see what is happening for that example? And now I've given you a visual understanding, intuitive understanding, as well as a coding understanding. In the code I have written the description of what is happening in every layer. For example, here you will see that the forward method takes a batch of input tokens, computes their embeddings, applies the positional embeddings, passes the sequence through the transformer blocks, normalizes the final output, and then computes the logits representing the next token's unnormalized probabilities. We will convert these logits into tokens and text outputs in the next class. But when you access this code file, I have also written a number of such comments and paragraphs here which you can read and try to understand the code for yourself. One thing which I will very highly suggest is that whatever I've written on the whiteboard, right, when I was myself writing the flow map of the transformer on the whiteboard, this flow map, I understood that my understanding also became very clear. If I just ran the code, my understanding was not that strong. But when I wrote every single step of the code on a whiteboard, and when I created a visual flow map, which I demonstrated to you in today's lecture, such kind of visual flow map which I am showing right now on the screen, it really strengthened my understanding and it made me confident about this subject. If you can also write this similar flow map on your notebook or on the whiteboard which you are using, it will tremendously improve your understanding. Thanks a lot, everyone. I hope you are enjoying from these lectures. Next lecture will probably be the last lecture in the GPT architecture series, where we'll generate text from the final output tensor which we have obtained today. Thanks a lot, everyone, and I look forward to seeing you in the next lecture.